Hey, NA Physics, it's Mr. Neff. Let's do our introduction to lenses today. But before we do, did you hear that the candle quit his job? I'll tell you why at the end of the video. So similar to spherical mirrors, spherical lenses are ones that you get the shape of it from a sphere. Now with a mirror, it was just a piece of one sphere. With the lens, it's going to be a piece of two spheres most of the time. You could take two spheres like we have here on the left, and I have two spheres that are overlapping, sort of like a Venn diagram. If I took those spheres and I filled that space with glass, I would get a shape over here that was part of this sphere on the right, and I'd get this shape over here that was part of the sphere on the left. That would be a spherical lens. I could do it differently too, where the two weren't actually overlapping, but I just fill the space in between them, or some of the space in between them, with glass. And now you'd see that this side belongs to the sphere on the left, and this side belongs to the sphere on the right. It gives you two very different shapes. You can see that the one on the left gives you a shape that's thicker in the middle than it is on the edges. We're going to call that a converging lens. And we're going to have the shape on the right is going to be thinner in the middle than it is on the edges. We're going to call that a diverging lens, as you can see there at the top. Now, the converging lens is important because incoming light rays that are parallel all get focused to a focal point. This picture, more than anything else that I'm going to show you in this video, is extremely important for you. So I would jot this down. So here come these parallel light rays. They're coming in like this, all parallel to this principal axis. They hit the lens, and they bend a little at the first surface, they bend a little at the second surface. Look at that dispersion video, and it'll show you some of that. And it's going to focus right here at this focal point. That makes it a converging lens because it is converging the light. Some people call that a convex lens too, and that's not the wrong thing to call it. But in a second, I'm going to show you something that says the lens doesn't always look just like that with two convex sides if it's converging. And so that convex, I know, is a little dangerous, so I'm encouraging you to call it converging and not convex as much. Just as important as that picture is this picture for the diverging lens. Again, you could call it concave, but that's a little dangerous. I'm going to call it diverging. So you can see here, same premise. I have these parallel light rays parallel to that principal axis. But this time, whenever they hit the lens, they're going to get bent, refracted in a way so that they are never going to cross again. Not just that, but they look like they all came from this focal point. Did they? No, they all came in parallel. Most of them, none of the ones, in fact, pictured here, went through that focal point. But to the observer standing over here, they all seem like they came from that focal point. Now, you can have lots of different shapes for converging and diverging lenses. All the lenses on the left three, they are all converging. Notice something. They are very, very different at first glance, but they're similar in that in their centers, they're all thicker than they are on their edges. Thicker in the center than it is on the edge. Even this one that looks kind of contact lens-like, is thicker in the middle than it is on the edge. These, on the other hand, are thinner in the middle than they are on the edge, and that makes these diverging lenses. See, thin in the middle, thicker on the edge. Thin in the middle, thicker on the edge. Thin in the middle, thicker on the edge. And in fact, if you're a contact lens wearer and you're a teenager, chances are this is what you have. If you are an eyeglass wearer and you're a teenager, chances are this is what you have. All that is to say that these two kinds of lenses, they do very, very different things. If the lens is thick in the middle, it's converging, and it's going to take that light and make it go to a focal point. It's going to converge it. If it's thin in the middle, it's going to be diverging, and it's going to make that light go away from each other, but it's going to seem like it all came from one point. Now, just like with mirrors, we have sign conventions with lenses. And you could look at it in a table like this, and you could say, well, at this time, this length is going to be positive, or that image is going to be a negative, and so forth. And that's fine, and you can come back and pause the video at that point if you want. But can I just give you an easier way to remember this? Now, if you remember, this is a plane mirror, so just a touch of review. If you're looking at a plane mirror, if we're looking at an object in a plane mirror, you're going to be out here on this side. And so here's our object, this dark blue one, and we have the DO, and it's measured that way, and we call that positive. Here's the image, it's back in the mirror, and because it was back there, we said that that was a negative DI. Here we go. The DI was negative when it was on the other side of the mirror from the observer. Yeah, it's true that the back side of the mirror was the negative side and the front side of the mirror was the positive side. But if you remember our video on mirrors, the reason that was the case is because the observer was on this side. That's what made it positive. And the observer was not on this side. And so that's what made that back side negative. And that same thing happened with the curved mirrors. And so I'm looking at an object in a convex mirror. Here I am as the observer, and here I have my DO, and it's positive, and then there's my little baby image, and it's a DI, and it's back in there, so it's negative. Sometimes I had a positive DI. Here is the image formed from a concave mirror, and so here's my positive DO, and at the same time, here's my positive DI. Positive this time was because the DI was on this front side of the mirror, yes, but more than that, because it was on the observer's side of the mirror. Versus here we have that same kind of mirror, but this time you have the object real close, so you still have that positive DO, but the image is back in there, and so it's a negative DI. And so with a mirror, it's tempting to say front side of the mirror, positive, back side of the mirror, negative. And that works, but why does it work? Because the observer is on the front side of the mirror, and the observer is not on the back side of the mirror. Well, so similar with lenses. Now, with a lens, you're going to have an object, you're going to have an image. And I'm going to show you in the next videos how to draw these objects and images. But all that is to say this, the observer with a lens is not going to be on the same side of the object. If you're looking at something with a lens, you're looking at something through the lens. And so just for this first picture, if I were going to observe this, I would be standing here. Now, don't look at these for now. I'm going to be standing here. I'm going to be looking at the object through the lens. And so just like before, almost every time we're going to call this a positive DO. But here's the difference. Now, if the image is formed over here, and I'll show you why that's the case in the future. But if the image is formed over here, we're going to call that a positive DI because it's on the other side of the lens than the object? Well, sort of, but mostly because it's on the side of the lens of the observer. Now, in contrast to that, look at these. On these, we're going to have an object and an image that are going to be on the same side. So say I'm looking at this middle picture. And here I am as the observer, and I'm looking at this object, that darker one, through the lens. And so this is going to be a positive DO, but now this is on the same side, and it's not the observer's side. And so that's going to make that a negative DI. Now, even though that sign convention is slightly different than what we had for mirrors, there's going to be the same sign convention as we had for mirrors for the heights. For instance, you can see there's a principal axis that goes through each one of the pictures. Principal axis, just like I had before. And if you're measured up here on this side, this top side of the principal axis, we'll call that a positive height side, call that a positive HO. This has an image height that is down like this, and so just like I did before, I'll call that a negative image height. Over on the second picture, again, I have a positive object height, and now I'm going to have, since it's measured up, a positive image height too. And remember, the positive image height on mirrors stood for an upright image. Well, it stands for that same upright image now. In the next video, we'll talk about how the sign conventions work with ray diagrams, and it used to be the mirror equation. It'll now be the thin lens equation. So watch the next video for that. And so did you hear that the candle quit his job at the factory? He was just burned out.